I think what separates people who seem quick and adept with mathematical problem solving from those who are not yet as fluent is not some notion of genius or innate insight. My bet is that the people who seem quick have just spent a lot more time exposed to the kind of patterns that often arise in puzzles, with more total hours logged where their minds were mulling over associations between these patterns. And the goal of this video here is simply to expose you to a very important set of patterns that come up a lot in probability, those associated with the function n choose k, whose values often go by the name binomial coefficients. For example, take a look at this pattern right here. Every line is a string of 5 digits, including exactly 3 ones and 2 zeros. I've written it out pretty systematically, so you can probably convince yourself that this includes all possible strings of 5 bits with exactly 3 ones. And in total, if you count them, there are 10 of them. Given 5 available slots, the number of ways to choose 3 of them to be ones turns out to be 10. The way this is often conveyed in math is to say 5 choose 3, written as a 5 over a 3 inside 2 parentheses, equals 10. But I don't want you to think of 5 choose 3 as just being a number. Really hold in your mind this pattern of all of the ways you can fill 3 out of 5 slots. As another example, this right here is what 6 choose 3 looks like. Again, I like to think of strings of zeros and ones, this time with 6 total bits, 3 of which are ones. But the zeros and ones here are just a way to capture the idea of having 6 options and choosing 3 of them. In this case, the total number comes out to be 20. So you'd say 6 choose 3 equals 20. And I'll talk about how you compute these numbers in just a few minutes, but you'll have a richer understanding of what 6 choose 3 is all about if the image that comes to mind is this pattern here and the sensation you have while looking at it, rather than just the number 20. I say this because what's a lot more important than computing the numbers is being able to recognize when they are needed, when you're faced with some puzzle in a totally different context which has one of these patterns at its heart. So the more you let your mind mull over it and get a feel for what it's all about, the more primed it's going to be to recognize when n choose k pops up in a problem-solving context. To give an actual probability example, suppose you choose 5 people at random. And for the moment, let's say that each one has an equal chance of being a man or a woman, independent of the other choices. And what you want to know is the probabilities that your randomly selected group will have 0 women, that it'll have exactly 1 woman, that it'll have exactly 2 women, etc. Well, for any probability problem, it's a good idea to start by getting a feel for what all of the possibilities look like. Here, there's 2 possibilities for that first person, man or woman. And each of those cases subdivides into 2 more, based on the gender of the second person. Each of those gets subdivided into 2 possibilities, based on the third person, and so on. And in total, what we're going to be left with here is 2 times 2 times 2 times 2 times 2, or 32, possible configurations. Let's go ahead and clump all of these 32 configurations into groups based on how many women each one has. And what you'll find is only 1 includes 0 women, that's 5 choose 0. 5 of these configurations have 1 woman. Those with 2 women are a little harder to think about at first, but as we saw earlier, you can count that there are 10 of them, that's 5 choose 2. Symmetrically, there are 10 with 3 women, since you can also think of those as the configurations having 2 men. Likewise, 5 of them have 4 women and 1 man. And only 1 configuration has 5 women. And now, there's a sensation I want you to remember here, that the total number of possibilities was a power of 2, but they naturally clumped up into this 1, 5, 10, 10, 5, 1 pattern. That sensation arises enough in the context of probability that it's worth remembering. Now, the answer to our original question is sitting right here. Assuming all of these patterns are equally likely, there's a 1 out of 32 chance you end up with 0 women, a 5 out of 32 chance that you end up with exactly 1 woman, a 10 out of 32 chance that you have exactly 2 women, and etc. And in the spirit of immersing ourselves in more patterns, there's a really nice way to think about how these numbers 1, 5, 10, 10, 5, 1 are built up from smaller cases. Let's consider what all this looks like for groups of 4 people. There are 2 to the 4th, or 16 possible configurations of men and women, and if we clump them up like before, only 1 of them has 0 women, 4 of them have 1 woman, 6 of them have 2 women, 4 have 3 women, and 1 has 4 women. So we have this nice 1, 4, 6, 4, 1 pattern. Now, if you were to add a 5th person onto this, there's 2 possibilities. Either you add a man, so the number of women in each configuration doesn't change, or you add a woman, in which case you might think of shifting each configuration over to indicate that the total number of women in each one has increased by 1. And what that means is taking 2 copies of this 14641 pattern with one of them shifted over and adding up the corresponding terms, we get the pattern that we saw earlier for groups of 5 with these 1, 5, 10, 10, 5, 1 clumps. And in fact, backing up further, you can think of everything as being generated from a really simple case, like having just one person. And as we add one more, this splits into 2 possibilities based on the gender of the added person. Duplicate it, shift one of them over, and add things up. And if you let this play out a little bit, duplicating, shifting, adding up, there's some numerical niceness at play. First off, organizing the numbers that you get into a triangle, this is the famous Pascal's triangle. Usually this is introduced by saying that each number is the sum of the 2 above it, which is the same thing as saying that each row generates the next one by taking 2 copies of itself, sliding one over, and adding up the aligned terms. But this is not just about playing with numbers. Keep at the forefront of your mind what each one of these actually mean. For example, if you go down to the 9th row, and then count in from the left 0, 1, 2, 3, 4, this number right here, 126, represents 9 choose 4, which you might think of as how many configurations of 9 people include exactly 4 women. How many ways can you choose 4 out of those 9 options? Phrased as a probability example, you could say that for a random collection of 9 men and women, where each gender has an equal chance of being chosen, there is a 126 out of 2 to the 9th probability of including exactly 4 women, which in this case is about a 24.6% chance. Also, this triangle might look a little strange if we don't cap it off with a 1. You can think of this as representing how many configurations of 0 people include 0 women. I mean, there's only one configuration of 0 people, nothingness, and nothingness does indeed include 0 women. And here's something else worth noticing. As you keep applying this process, maybe representing the numbers as the heights of bars, things tend towards this really nice bell shape, which turns out to be a very important shape in probability. So, as I've probably overstated by this point, when you think of something like 5 choose 3, I'd encourage you to think of this pattern, and vice versa. But I should mention that there's a more common way of introducing the topic. A typical example might be to imagine 5 people, say Ali, Ben, Cam, Dennis, and Evan, and ask, how many ways can you choose 3 of them? These are really 2 ways of saying the same thing. For every string of 5 zeros and 1s, you could imagine lining up these bits over the 5 people and selecting those people underneath the 1s. Every possible string of zeros and 1s gives us a unique subset, and every subset gives us a unique string of zeros and 1s. And in doing this, by the way, notice how the triplet Ali, Ben, Cam is considered the same thing as Ali, Cam, Ben, or any other way that you might choose to order them. So it's common to say that n choose k counts subsets of size k, where order doesn't matter. But a phrase like order doesn't matter can be kind of confusing, because back in the context of binary strings, order most certainly does matter. After all, these are all the different ways to order 3 1s and 2 zeros. It's just that the sense in which order doesn't matter for binary strings is that saying the first, the second, and the 5th bits should be 1 is the same thing as saying the second, the 5th, and the 1st bits are 1. It doesn't matter how you list those placements. Nevertheless, I've seen students get confused when they lean too heavily on language to remember what n choose k means, which is why I recommend bringing to mind this image of binary strings. I think it's just a lot less ambiguous. Now, many probability puzzles involve choosing a subset like this. For example, you might say, what's the probability that when you choose 3 people at random from this group, one of those 3 people is Ali? Well, there's 5 choose 3 total possible triplets, which is 10. And then how many of them contain Ali? Well, if you know Ali is in the batch, then you have to choose 2 from the remaining 4. So that's 4 choose 2 remaining options, which we saw earlier as 6. So it's a 6 in 10 chance that a randomly chosen triplet contains Ali. But you might be wondering at this point, how do you actually compute these things? Is there a faster way than just writing out Pascal's triangle? And luckily, thinking of n choose k as counting subsets does lend itself to a nice way to think about computing it. If we stick with our example of choosing 3 people from a group of 5, start by counting as if order actually does matter, as if there's some notion of who in your triplet is first, who is second, and who is third. When you do that, there are 5 possibilities for who that first person is. Then once he's chosen, you have 4 remaining choices for who can be second, and after that, only 3 people left who could be your third. So that gives 5 times 4 times 3 total possible ordered triplets. And of course, that is way overcounting 5 choose 3, because a triplet like Cam, Ben, Evan shows up multiple different times when we count all of its orderings differently. So as a second step, to see how badly you've overcounted, how many ways are there that you can order a particular subset, like Cam, Ben, and Evan? Well, there's 3 choices for who could go first, which leaves 2 choices for who could go second, and that just leaves 1 choice for who goes last. In other words, it's 3 factorial, or 6. To visualize what's going on, here are all of the ordered triplets that you could choose, which is what that numerator 5 times 4 times 3 represents. And you can think of these as coming in groups of 6, where each such group represents all the particular permutations of a given unordered triplet, the thing that 5 choose 3 is supposed to count. So that is 60 divided by 6 total unordered triplets, which is 10, like we saw before. To do another example, let's compute 9 choose 4. Again, just to beat this dead horse one more time, the pattern that should come to mind is all the strings of 1s and 0s, including exactly 4 1s. This somewhat monstrous collection, which does have some rhyme and reason as you look into it, is what 9 choose 4 feels like. But to compute it, think about choosing 4 items from a group of 9. There's 9 choices for that first item, leaving 8 choices for the second, times 7, times 6. And as before, this is way overcounting, since a subset gets counted many different times based on its permutations. So to account for that, you count how many permutations are there for a subset of size 4, which is 4 times 3 times 2 times 1. And we'll just divide out by that. What's very pleasing whenever you do this out by hand is that there's always a lot of cancellation that happens between the numerator and denominator. And in this case, you're going to be left with 9 times 2 times 7, which is 126, as we saw earlier in Pascal's triangle. Now, I like to think about this formula as kind of a weird form of cancellation, where whenever you count something by multiplying successive numbers like this, you have 5 choices, then 4 choices, etc., implicit in that is the assumption that order matters, that ABC is counted differently from BCA. So to make up for that, you divide out by something that also involves a similar sort of successive multiplication. The denominator is saying, for a given subset of 3 people, how many ways can you order them? So it's similar to unit cancellation between the numerator and the denominator, but here the thing being cancelled out is the premise that order matters. At least loosely speaking, that's obviously vague. Now there's something pretty striking about this formula that would be a shame not to mention. Take a look back at that 1 5 10 10 5 1 pattern that we had earlier, describing how all 32 of the 5-bit strings get clumped up. If we write this out as 5 choose 0, plus 5 choose 1, plus 5 choose 2, and so on, and then expand out each one of those based on the product formula that I just showed, it is not at all obvious that that should necessarily be a power of 2. I mean, really, the more you stare at this expression or the generalization of it, the more striking it is. It's a good example of how when you mix 2 different perspectives for how to count the same thing, some really interesting math can pop out of it. Now I mentioned way at the start that these are often called binomial coefficients, and if you want to see why, I highly encourage you to right now pull out a piece of paper and play around with expanding expressions like x plus y squared, x plus y cubed, and so on, if it's something that you've never done before. These expressions are called binomials since they have 2 variables, and you'll notice that the terms which arise are the same numbers that we've been playing with here, and the reasons which they arise have the same sensations as the patterns that we've been looking at here. Really, if you've never done it, it is a great way to build intuition. One important context where this pattern comes up is something called the binomial distribution, foundational to a lot of probability, and that's what I'll be talking about next video. See you then!